Good morning, good afternoon, good evening. This is your Professor T. Freed Muhammad. This is the third addendum lecture for Marshall University, West Virginia's quantum computing teaching. How quantum computers can find one hidden answer faster. So imagine you walk into an enormous library, but this is not an ordinary library. There are no shelves, no alphabetical labels, and no search box. Instead, you see thousands, perhaps millions of identical doors. Behind exactly one door is the book you need. A classical computer would solve this problem in the most straightforward way. Open one door, look inside, close it if the book is not there, and move to the next. That works. But if there are a million doors, we may have a very long day. Quantum computing asks a different question. Can nature itself help us search differently? Today, we are going to explore one of the most famous algorithms. In reality, one of the most famous answers to that question, Grover's search algorithm. And throughout our journey, imagine that our student explorer Maya is standing inside this strange library of million doors, trying to find one hidden answer. Before Maya begins opening doors, she needs to understand what kind of problem she's facing. Our goal today is not simply to memorize a formula. I want you to understand the idea well enough that you could explain it to someone else. By the end, we should be able to compare classical search with quantum search, understand superposition, understand what an oracle does. This is not the Oracle database, by the way, just FYI, or Oracle Foundation. Understand how amplification changes the odds, estimate the number of qubits and iterations required, and recognize the basic shape of a Grover circuit. There is no one simple pattern. I want you to remember this. Look, tag, boost, check. Maya will first represent all possible doors. Then the quantum system will tag the correct one. Next, it will boost that answer. Finally, Maya will check by measuring that four-part idea, the look, tag, boost, and check. That is the heart of our discussion. Now imagine Maya asks the librarian, can you tell me which section the book is in? So what kind of a search are we talking about? That's a great question, right? The librarian says there are no sections. Can I sort the doors? The answer is no. Is there a clue based on the door number? The answer is no. The only thing Maya can do is choose a door and ask, is the book behind this one? The answer is either yes or no. That's still binary, by the way, just FYI. This is called an unstructured search problem. There is no useful order that allows us to eliminate half the possibilities the way we could with a sorted telephone directory. If you're old enough, you might have seen that. But if you are not that old enough to know what is a telephone directory, go ask someone who is older enough to understand the word telephone directory. That used to be a book. Grover's algorithm is designed for this kind of situation. That distinction matters. Grover is not automatically faster for every search problem. It is especially interesting when there is no better structure available and we have some test that can tell us whether the candidate is correct. One by one classical search. Let's first send a normal classical computer into Maya's library or a standard binary agent. It checks door number 1, wrong, door number 2, wrong, door number 3, wrong, and it keeps going. If there are n possibilities, the worst case could require almost n checks. If the answer is randomly located, a rough average is around n divided by 2. There is nothing unintelligent about this method. In fact, sometimes it is exactly the correct classical strategy, but here is the problem. The work grows directly with the size of search space. If the library becomes 10 times larger, we may perform roughly 10 times as much work if it becomes 100 times larger, roughly 100 times as much. Maya looks down the endless hallway and realizes that simply becoming faster and opening doors may not be enough. She needs a different idea. 3 quantum ideas. Let's discuss all these. Before Maya can use that different idea, she has to enter the quantum part of the library. Here we need 3 concepts. First, a qubit. A classical bit is normally either 0 or 1. A qubit can be prepared in a quantum state that involves both possibilities. Second, superposition. This allows the quantum system to represent a combination of possible states before measurement. But be careful, this does not mean we can simply read every answer simultaneously. Measurement will still give us one result. And that brings us to our third concept, measurement. Measurement converts the quantum state into classical result that we can actually read. So Maya's challenge becomes very interesting. If measurement gives only one answer, how can quantum computing help? The secret is before measuring, we change the probabilities. How many items can qubits represent? Maya now needs a numbering system for the doors. Quantum computers use binary labels. With one qubit, we can represent 2 labels 0 and 1. With 2 qubits, we can represent 4 labels 0 0, 0 1, 1 0, and 1 1. 3 qubits give us 8 possibilities. The pattern is 2 to the power n possibilities for n qubits. This is one of the first calculations we make when designing a quantum search. For example, 5 qubits give us 32 binary labels because 2 to the 5th power is equal to 32. Notice what is happening. We are not storing 32 complete books inside 5 qubits. Instead, a qubit register provides 32 possible labels or states that every circuit can work with. Maya is essentially giving every door in the library a quantum address. Now we can prepare the entire collection of addresses for searching. Changing the odds before looking. This slide contains one of the most important ideas in the entire lecture. Quantum states have something called probability amplitudes. You can imagine an amplitude as something like the height and the direction of a wave. When we measure, the probability of an outcome is related to the square of its amplitude. At first, Maya gives every door an equal chance. Picture thousands of identical waves standing at exactly the same height. But Grover's algorithm begins manipulating those waves. The waves can interfere with one another. Some become smaller, others become larger. And eventually the wave connected to the corrected answer can become much taller than the others. This is a real quantum advantage. Grover does not magically reveal the answer. Instead, Grover engineers the probability landscape so that when Maya finally looks, she is much more likely to see the correct door. The four main stages. Now we can see the map of Maya's journey. First, initialize. We place the qubits in a known starting condition, usually all zeros. Second, create superposition. Hadamard gate, spread the quantum state across all possible labels. Third, use the oracle. The oracle recognizes the correct answer and marks it in a special quantum way. Fourth, use diffusion. Diffusion takes the hidden mark and turns it into something useful by increasing the amplitude of the marked state. And here is an important vocabulary point. Oracle plus diffusion equals one Grover iteration. We may repeat that pair several times, then we measure. So if you forget every complicated circuit symbol later, remember the basic rhythm. Prepare, spread, mark, amplify, measure. Now we are ready to enter the strangest room in Maya's library. I have utilized a terminology, Hadamard gates. I would strongly suggest you to look into that to learn more in your quantum computing learning journey. Let's move on. Initialization and superposition. Maya enters a circular room containing a control panel. Every quantum switch begins at 0. There is one initialization step. The qubits typically start in the state, and we write as you can see the pipe, the 0, and the greater than sign. Then Maya presses a set of buttons marked H. There are Hadamard gates, as I mentioned earlier. After the Hadamard gates operate, our qubits enter superposition. Instead of our register representing just one binary label, the quantum state now contains amplitudes associated with every possible label. At this moment, none of the doors is preferred. Every candidate begins with equal probability, and that fairness is important. Grover does not begin by guessing which answer is correct. It begins by treating the possibilities equally and then uses the structure of quantum interference to reshape these probabilities. Maya now has spread her attention across the entire library, but she still needs some way to identify the correct door. The oracle marks the answer. This is where our story inside the story begins. The librarian tells Maya an old story about a place called the City of Lanterns. In that city, thousands of lanterns look identical. One lantern contains a hidden blue flame, but from outside you cannot see which one. A mysterious lantern keeper can walk through the city and perform one special operation. When he reaches the correct lantern, he turns its wave around. He does not make it brighter, he does not announces its location, he simply gives it a hidden quantum mark. That is essentially what the oracle does. For the correct state, it changes the phase, often represented as a sine flip of its amplitude. But there is a strange part, or I can say here is the strange part. If we measured immediately after the oracle, the answer would not suddenly have a huge probability. The lantern keeper has marked the right lantern, but Maya still needs a way to turn that invisible mark into visible advantage. That is the job of diffusion. Diffusion amplifies the answer. The lantern keeper continues his story. After reversing the special lantern's wave, he strikes a giant bell in the center of the city. The sound waves travel outward, reflect the interference with the waves of every lantern. Because one lantern was previously marked differently, this interference affects it differently. Its wave grows. The others become slightly smaller. The bell is our story version of the diffusion operator. Mathematically, diffusion is often described as a reflection about the average amplitude. You do not need to visualize every equation yet. The important point is what it accomplishes. The oracle creates a difference. Diffusion amplifies a difference. So Maya now understands the two-part engine of Grover's algorithm. The oracle whispers, "This one is different." Diffusion responds, "Then let's make the difference bigger." And each time they repeat the sequence, the correct answer becomes more likely to appear when measured. How many Grover loops? So Maya is excited. She says, let's repeat the oracle and diffusion thousands of times." The librarian immediately stops her. "Quantum algorithm has timing. For one marked answer, the number of Grover iterations grows approximately with the square root of n. A more accurate expression includes the factor pi over 4 and can also account for multiple correct answers. The big idea is the comparison. Classical unstructured search requires work proportional to n. Grover's requires work proportional to approximately square root of n. Suppose our research or search space contained 1 million possibilities. A classical search might need work on the scale of hundreds of thousands of checks. The square root of 1 million is only 1,000. That is an enormous mathematical difference. But notice, 1,000 is not zero. Grover does not make search instantaneous. It gives us what is called a quadratic speedup. And as our library grows, that difference becomes increasingly important. Why the square root matters? Look at the shapes of these two growth patterns. The classical line represents or climbs rapidly because the work grows with n. Grover's search is much gentler because the number of iteration grows approximately the square root of n. Imagine Maya's library expanding. This is a significant, important topic. I'm going to reiterate myself on the slide 13 why the square root matters. Once again, look at the shapes of these two growth patterns. The classical line climbs rapidly because the work grows with n. Grover's growth is much gentler because the number of iteration grows approximately the square root of n. The repetition of this discussion is for me to iterate and reiterate that this is a profound information you must concentrate on. Imagine Maya's library is expanding. At first there are 100 doors, then 10,000, then 1 million, then 10 million. As the library becomes larger, the difference between n and square root n becomes dramatic. This is why complexity matters in computer science. Sometimes the real breakthrough is not simply building a processor that performs each operation faster. The breakthrough is discovering an algorithm that requires fewer operations as the problem grows. Maya has discovered that Grover does not win because it runs through the hallway faster than a classical computer. It wins because it follows a completely different mathematical path through the problem. The circuit view. Now let's leave the story for a moment and look at how this appears in a quantum circuit. A circuit is simply a recipe. The horizontal lines represent qubits. We first prepare those qubits. Then we normally place Hadamard gates on them to create superposition. Next comes the oracle. After the oracle comes the diffusion operator. And finally, after repeating the Grover loop, the appropriate number of times we measure. So when you see a Grover circuit for the first time, don't let a complicated diagram frighten you. Look for the major landmarks. Ask yourself, what are the qubits prepared? Or where are the qubits prepared? Where is superposition created? Where is the oracle? Where is diffusion? Where is measurement? Once you can identify those pieces, even a complicated circuit becomes to tell a recognizable story. Reading the circuit left to right. Quantum circuits are generally read from left to right. Think of each horizontal line as a character moving through our story. Qubit 0 follows its line. Qubit 1 follows another. Qubit 2 follows another. Where a line passes through an H gate, a Hadamard operation occurs. When all the qubit lines enter the oracle block, the oracle evaluates the candidate states and marks the correct ones by phase. Then they pass through diffusion, where amplitude amplification occurs. The oracle and diffusion blocks may repeat. Finally, the meter symbols represent measurement at the point the quantum part of our story ends and we receive ordinary classical bits. This is important. A quantum computer must eventually give us a classical result that a human or conventional computer can use. Maya's strange journey through waves, phase, and interference must ultimately end with something simpler, a door number. Now the librarian changes the rules. Maya, he says, what if 4 doors contain acceptable books instead of only one? That actually makes the search easier. If there are m correct answers among n possibilities, the approximate iteration count depends on the square root of n divided by m. As m increases, n divided by m becomes smaller, so fewer Grover iterations are required. Return to our city of lanterns. Instead of one hidden blue flame, imagine 4 lanterns contain blue flames. The lantern keeper marks all 4. Diffusion then amplifies the group of marked states. When we measure, we do not necessarily know which one of the 4 we will receive, but we have a high probability of receiving one of the correct answers. This makes intuitive sense. If several answers satisfy one requirement, there are more successful destinations available. Why more iterations can hurt? Here is one of Grover's most surprising lessons. More computation is not always better. Imagine Maya walking toward the correct door. Each Grover iteration turns her closer toward it. After several turns, she is almost directly facing the answer. That is the moment to stop. But suppose she keeps turning. She passes it. Now she begins moving again, or moving away again. Grover's algorithm behaves somewhat like this mathematically. The probability of the target rises, reaches a high point, and can then fall if we continue repeating the operation. This is why choosing the iteration count matters. Quantum algorithms often depend not just on what operations we perform, but also on how many times and when we measure. Maya learns an important lesson. Success is not about repeating the algorithm forever. Success is about knowing the right moment to look. Where could Grover be useful? Now we can ask the natural question, what could we actually search for? The answer is broader than a library. Suppose we are searching possible cryptographic keys, or look for a configuration that satisfies a set of rules, or searching candidate solutions in an optimization problem. or using Grover style amplitude amplification as one step inside a larger scientific algorithm. The common feature is that we need a test. Given a candidate, can we construct an oracle that says yes, this satisfies the condition, or no, it does not? That is crucial. Grover is not a magic search box into which we dump any database. The problem must be represented in the form of quantum circuit can evaluate. Maya realizes that the mysterious oracle was never magic. Someone had to design it. And in real quantum computing, designing that oracle can be one of the hardest parts. Why we don't use this everywhere today? At this point, Maya asks the obvious question. If Grover is so powerful, why is not every search engine already quantum? Because knowing an algorithm and having the technology to run it at useful scale are two different things. Today's quantum machines face noise and errors. Useful algorithms may require many reliable operations, and physical qubits are not the same as perfectly reliable logical qubits protected by quantum error correction. The oracle itself can also require a large, complicated, reversible circuit. And there is another practical problem. Data does not magically appear inside a quantum computer. If loading or encoding the data requires too much work, a part of the theoretical advantage may disappear. So Grover teaches us two lessons at once. It shows the extraordinary possibilities of quantum algorithms, but it does also reminds us that engineering matters. A beautiful mathematical speed up must eventually survive real hardware. Practice the method. Now imagine Maya gives you the key to the library. Can you think like a quantum search designer? If you have a certain number of possible labels, first ask how many qubits are needed. Then estimate the square root of the search size to understand the scale of the Grover loop. Then ask, what does the oracle actually test? And perhaps most importantly, can you explain why the oracle alone is not enough? Remember the lantern keeper. Marking the special lantern did not make it brighter. The mark had to interact with diffusion. Then try sketching the process. Hadamard, oracle, diffusion, measurement. Finally, ask yourself, what might prevent your design for becoming a practical machine today? If you can reason through those steps, you understand Grover much more deeply than someone who only remembers the formula square root of n. Common mistakes. Before Maya leaves the librarian gives her three warnings. First, never say the quantum computer checks every answer and then simply reads all of them. Quantum mechanics does not allow us to measure a superposition and receive every stored possibility. Grover works by manipulating amplitude so that one useful answer becomes more likely. Second, never give the oracle too much credit. The oracle marks the answer by phase. Diffusion converts the mark into increased probability. And third, never assume more iterations are always better. Grover has an optimal stopping region. So when explaining the algorithm, follow the sequence. Start with the search problem. Determine the qubits. Create superposition. Apply the oracle. Apply diffusion. Repeat an appropriate number of times. Then measure. That sequence keeps both our science and our story accurate. Maya finally stands before the correct door. She opens it. Inside is not just a book she was searching for. There is a note from the lantern keeper. It says, the secret was never seeing every answer. The secret was changing the odds before you looked. That sentence captures Grover's algorithm beautifully. Classical unstructured search grows roughly with n. Grover changes the scaling to approximately square root of n. Superposition gives us starting search space. The oracle marks the useful state through phase. Diffusion amplifies its probability. We repeat that pair near the optimal number of times and then measure. And although practical large scale Grover search will require much more capable, fault tolerant quantum computers and carefully designed oracles, the algorithm has already taught computer science something profound. Quantum computing is not simply a faster version of classical computing. Let me repeat myself again. Quantum computing is not simply a faster version of classical computing. It gives us new ways of thinking about information, probability, interference, and computation itself. So, when you remember Grover's algorithm, don't picture a computer frantically opening doors. Picture Maya standing quietly in the library of a million doors, changing the waves of probability until one door becomes far more likely than all doors. That is the power and the beauty of quantum search. Remember, Grover is not instant search. It is mathematically proven quadratic speedup for the right kind of problem. Happy learning. See you in the next lecture of quantum computing.